Make a folder for our projects. Open STM32 IDE. Select U folder as workspace. In first part, I am creating a project with a standard CMSIS layer. Click on Start New STM32 Project. In target selection page, write microcontroller name in part number box. Select STM32F103C8. Click Next. I name this project CMSIS1. You don't need to change any options. And targeted project type is STM32 Cube. Click Finish. Close .ioc file and open these folders. I selected targeted project type as CubeMX, so Cube IDE would add CMSIS file to our project. But other files are also added to our project that we don't need, so I'm going to delete them. Delete .ioc file and everything related to HAL library. Delete everything in INC folder. Delete syscall and sysmem. Go to a startup file. In reset handler, which is here, before branch to main, which is here, there is a branch to a function named system_init. If you right click on it and open declaration, it's in system.c file. Open this. Purpose of this function is clock configuration and some other things. But this is empty now and we can do these things later in main. I'm gonna delete branch to system_init in a startup.s file. Then I'm going to delete system file itself. Open CMSIS folder, device, ST, STM32F1, include. This is device peripheral access layer header file, the important file that we need to access peripheral registers. I'm going to move this file to device folder. Right click on this and move, select device folder and click OK. Now I'm going to delete ST folder because it's so crowded here. Now we have device and include folder in CMSIS folder. Then open main, delete everything, write a main function with an infinite while loop. CMSIS layer is just a bunch of header files. Wherever we want to use them, we have to include them. To include CMSIS header file in our main.c file, we just have to include this one. Compile the code. I forgot to delete IT file. Compile again. We have to modify header directories. Go to project, properties, C++ general, paths and symbols. I'm going to delete all and we're going to add new directories. Our header files are going to be in these three folders. Click on add, check is a workspace path, click on workspace, select folder. I added other two directories. Click on apply and close, and then compile the code. We have two errors from this file. Open device peripheral access layer header file. We want to change a scalability setting, click yes. If you check this one, outline is going to be disabled. If you uncheck this one, outline is going to be enabled. And now we can see content of our file in outline view. Click on this thing to find error source. We don't have system file anymore, but it's included here. We don't need it, and then compile again. No error and warning. Now we can use CMSIS layer in main.c file. In Project Explorer, click on main.c. Click on show in, include browser. In this view, you can see what files are included in our main.c file. I open everything. These are all the CMSIS files in our project. But when we say CMSIS, we actually mean these two files. Device peripheral access layer header file that we included in our main and core cm3.h. In CMSIS folder in include directory, there are CPU specific and compiler specific files which we don't need in this project. Delete what we don't need. What's left now is what's necessary. Next we're going to talk about device file, what's in it and how to use it. I'm going to do blink project with a standard CMSIS, and if I want green LED on blue pill to blink, I have to change these registers. To make editor font bigger, you can do Ctrl++. Set bit 4 in APB2ENR register to enable GPIO-C clock. Putting PC13 in output mode by setting bit 21 and clearing 20 in GPIO-C CRH register. To turn LED on and off, clear and set bit 13 of GPIO-C ODR register. Device file provides two things we need for changing peripheral registers value: pointers and bit definitions. I start with CRH. To change GPIO-C peripheral register, I use GPIO-C pointer. Open declaration. Now we are in device file. GPIO-C is a macro. It's a name for this constant pointer. Its value is GPIO-C peripheral base address, which is another definition. And its type is GPIO type def asterisk, which means asterisk pointer type would be GPIO type def. Right click on GPIO type def and go to open declaration. This is an structure type with 7 uint32 type members designed based on GPIO peripheral registers. Back to main. GPIOC is a pointer to an structure. Put arrow operator after it and you can access its members, which are GPIOC peripheral registers. I want to change CRH. To set bit 21 of CRH register, we have to do bitwise OR assignment with bit 21 mask, which is 1 left shift 21. Instead of writing bit mask ourselves, we can use definition from CMSIS. Bit mask for all bits of all peripheral registers is provided by this CMSIS file. To find bit mask, first write peripheral name, underline, register name, underline, bit name, then press Ctrl space. Mode 13 is bit 20 and 21. Bit 21 mask is defined GPIO CRH mode 13 1. This macro expansion would be 2 left shift 20, which is 1 0 left shift 20. It's like 1 left shift 21, which is bit mask for bit 21. To clear bit 20 of CRH register in GPIOC peripheral, first we write peripheral name, arrow operator, register name. We want to clear bit 20 in GPIOC CRH register. For clearing a bit, we do bitwise AND assignment operator with not of bit mask. And bit mask would be GPIO CRH mode 13 bit 0. This macro expansion would be 1 left shift 20, which is bit mask for bit 20. Then we use ODR to turn LED on and off. First you write peripheral name, arrow operator, then register name. Now we can access ODR as a 32 bit. To set bit 13, we do bitwise OR assignment operator with bit 13 mask, which is going to be 1 left shift 13. But there is a definition for this value in CMSIS file. Peripheral name, underline, register name, underline. We need bit mask for the bit 13. It would be ODR 13. Clear bit 13, we do bitwise AND with not of bit mask. Next step is adding delay function. I define a delay function before main, which is just a nested for loop, and I call it here and here. Every peripheral needs clock to work, and even for changing peripheral registers to take place, we have to enable peripheral clock first. To enable GPIOC peripheral clock, we have to set bit 4 in APB2ENR register in RCC peripheral. So first write peripheral name, then arrow operator. We want APB2ENR register. To set bit 4, we do bitwise OR assignment operator with bit mask, which would be peripheral name, underline, register name, underline, and then bit name. I press Ctrl space. We want to change bit 4, which is bit IOPCEN. IOPCEN is bit 4 of APB2ENR register. IOPCEN pose would be 4. And IOPCEN mask would be 1 left shift 4. IOPCEN is IOPCEN mask. So I choose IOPCEN. This was blink LED with a standard CMSIS. Compile the code. These pointers and bit definitions are provided for us by this CMSIS header file. This is a header file that has some tools to access our device peripheral. For each peripheral, there is a typedef structure with members of type uint32T, which are peripheral registers. Base address for each peripheral is also defined. We need a base address and a new type to make a pointer for each peripheral. For GPIOC peripheral, we have a pointer with type GPIO typedef asterisk and value of GPIOC base, which is base address of GPIOC peripheral. We use this pointer to access peripheral registers. To change register values, you also need bit mask. In peripheral register bit definition section, all bit mask for all registers are defined. In next part, we are going to replace device header file and use a better way to access our peripheral registers. To make a new CMSIS header file, I am going to use svdconf.exe, which is a part of Kale, so you have to install Kale. This program needs a special .svd file to make a new header file. We need svd file for STM32F1. You can download this file, but safer way is to download it with Kale. Open Kale, go to pack installer, search for STM32F1, click on F1 series. You have to install Kale STM32F1 XX DFP device family pack. If you install this, Kale will download our desired .svd file. Exit Kale. Go where you have installed Kale. I have installed it in drive C Kale v5 folder. In Kale v5 folder, we're going to search for our desired .svd file. Its name is STM32F103XX.svd. Here is our .svd file. As you can see, it's in device family pack folder. Copy .svd file. Now back to drive C and where we installed Kale. Go to UV4 folder. We paste our .svd file here because svdconf.exe, the program which we're going to use to generate our new header file, is here. So I needed .svd file to be in this folder. Now open command prompt. Putting command prompt on right and this folder on left. Copy UV4 folder address. In command prompt with cd command, we're going to change our directory to UV4 folder. To execute svdconf.exe program which is in UV4 folder, we just have to write its name and press enter. This is a header file generator that we're going to use to generate new header files. This is an example of header generation, and this is how we're going to use this program. First, we're going to write svdconf.exe, then one space. Then we're going to write name of our .svd file, which is stm32f103xx.svd. One space and then option. Option specifies what kind of header file we want to generate. Use this option, generate a structure for bitfield. Now press enter. Our new CMSIS header file is generated. If you use .svd file from unknown sources, there might be some error here. I'm going to copy our new CMSIS file to put it in our project. Open our workspace, go to our folder project, drivers, CMSIS, device. This is our old device header file and this would be our new one. In STM32Cube IDE, in driver folder, in CMSIS folder, in device folder, I'm going to change our old device file name to device old. When you check update references, this file references like this include is going to change to. Click OK. Right click on project and press refresh. Now you can see our new CMSIS header file that we added to our project. Rename it to device new. To replace device header file and make the new one usable, there are some tasks that we have to do. We want to replace device old file with device new, so core cm3.h and stdint.h must be included in new device file, and new file is going to be included in our main instead of old one. And there must be no file included in device new except stdint.h and core cm3.h. Go to device old file. At top of old file, after typedef enumerator, core cm3.h and stdint.h are included. Copy these two includes from old file. Open new device header file. After typedef enumerator, core ondef.h and system.h are included, which we have to delete. Paste includes that we copied from old file. Go to main.c. Instead of old file, include the new one. Next step is to modify typedef enumerator for interrupt numbers. In new file, typedef enumerator doesn't have numbers for CPU interrupts. As you can see, it starts from 0. Now go to old file, and this is IRQ type that we have to copy. As you can see, this one has Cortex M3 processor exceptions. These are CPU interrupts with negative interrupt numbers. Copy typedef enumerator and replace the enumerator in device new file. Compile the code. We have 6 errors and 2 warnings. Go to problems, errors. These 4 errors are about what we wrote in our main.c file. This error is about conflicting type for NVIC type. For NVIC peripheral, we have a type def, a pointer definition, and an address definition in our new device file and also in core cm3.h file. We have to delete NVIC definition in new file. So I'm going to delete this type def structure. NVIC base and NVIC also redefined, and we have to delete them. Compile again. We have 5 errors. Go to problems. None of these problems is related to our new device file. They are all in main.c. We solved NVIC redefinition problem. There is one problem left. We are going to discuss it later. So what is the advantage of this new CMSIS file? Both files provide a pointer for each peripheral. To make a pointer, we need a type and a value. For each peripheral, there is a type designed based on peripheral register map. This is what differs between these two files. In old file, to make pointer for GPIO peripherals, we use GPIO type def, which is a structure with 7 unsigned 32-bit member as GPIO peripheral registers. In new file, there is also a pointer definition for each peripheral. GPIO-A type is being used to make pointer for GPIO peripherals. GPIO-A type is a structure with 7 union members. Here registers are unions. Before, registers were just unsigned 32 bits. We have 7 unions for 7 GPIO registers. Each union has 2 members, one called reg and another called bit. These unions have 2 members because we want to be able to access this register as 2 types, with reg member as an unsigned 32 bit and with bit member as a structure with bitfield members. With bit structure we can access bits directly in C language. Each register is a union. This union has a member named bit. Bit is a structure with bitfield which is designed according to each register. New file provides pointer but no bit definitions, because with this file you don't need bit mask. We are going to be able to change bits directly without bit mask and bitwise operator. Now we are going to use our new device file. To change IOPCEN bit in APB2ENR register, first we write peripheral name, which is a pointer to a structure, then arrow operator, then register name. Now register name is a union. If we put dot after union, we can access its members. Now if I choose reg, I can access APB2ENR as a unsigned 32 bit. If I choose bit, I can access APB2ENR as an structure. To access bit structure member, put dot after it, and now we can access bits. I want to change IOPCEN bit. Now we don't need bitwise operator, and we can just write the value we want in IOPCEN bit. We want to set this bit, so we write 1 to it. To change mode 13, we're going to write first peripheral name, then arrow operator, then register name, which is a union, then we put dot after it. I choose bit, then we put dot. I want to change mode 13. Mode 13 should be 10, which is 2 in hex. ODR is also a union. I choose bit, then I choose ODR 13. In this line, we just want to set this bit. I write 1 to it. And in this line, I want to clear ODR 13 bit, so I write 0 to it. Compile the code again. This is blink LED with modified CMSIS access layer header file. There are still some problems with our new header file. The solution to our problem would be bitfield padding. To show you where the problem is, we have to change a bit in DMA1 and flash peripherals. Before changing any DMA1 registers, we have to enable its clock. My goal here was changing any bit in DMA1 and flash peripherals. It doesn't matter which bit we are changing. The special thing is about these peripherals and also GCC. Compile the code and go to debug session. In editor view, you can see our code in C language, and in disassembly view, you can see our code in assembly language. For each C line, you can see corresponding assembly instructions here. All of these lines in C code are about changing a register value. In assembly, this is done in 3 stages. First step is to copy peripheral register value from peripheral memory to one of CPU registers. This is done with LDR instructions. Second step is modifying value. Third step is copy modified value from CPU register to memory, which is done with STR instructions. First step takes 2 LDR instructions because we have to load peripheral register address in memory with first LDR, then loading peripheral register value with second LDR. Press I to run code instruction by instruction. Now if you press a step into or F5, one assembly instruction is going to be executed. I press F5, 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 go ahead, and there is no problem here until we reach this LDRH instruction. If I press F5 now, we are in line 115 in a startup.s file, and this is a branch instruction to this label. So when this instruction gets executed, CPU goes to infinite loop address, which is here. Infinite loop is actually address for this instruction. So this instruction branches to itself. It's an infinite loop. Reset the code. LDR instruction copy a word from an address in memory to a CPU register. LDRH instruction copy a half word from an address in memory to CPU register. LDRB instruction copy a byte from an address in memory to CPU register. There are also STR and STRH and STRB instructions. They copy a value from CPU register to memory. A fault happens when executing LDRH instruction on one of DMA1 registers because there are restrictions about how you can load or store values to some part of memory. For DMA peripherals, you can only use LDR and SDR. It means you just can load and store words or 32 bits. If you do otherwise, a fault would happen and code execution is going to stop. But for RCC peripheral, LDRH and SDRH is not going to be a problem. For this fault, DMA peripheral is not the only one to blame. If you compile this C code with ARMCC in Kale, there is not going to be a problem, and all of these instructions are going to be LDR, no LDRB and no LDRH. And all of these would be SDR. It's GCC compiler that uses different instructions for load and store on different registers. Why GCC does this and how can we control it? Access for CCR1 register is LDRH, for ACR register is LDRB, and for CRH register is LDR. If access to these registers is implemented differently, there must be a difference in their structure design. Starting with flash ACR, access to this register is with LDRB and SDRB. Click on ACR, open declaration. This is a 32-bit register, but just 6 bits are used. If sum of bit fields in a structure is equal or less than 8, loading and storing is going to be implemented with LDRB and SDRB. Next step is CCR1 register. Open declaration. For DMA CCR1 register, sum of bit fields is 15, which is bigger than 8 and equal or less than 16. So implementation is LDRH and SDRH. Next step is AHPENR. For RCC AHPENR, sum of bit fields is 11, which is bigger than 8 and equal or less than 16. So implementation is LDRH and SDRH. These nameless bit fields are also counted. They are padding for reserved bits. For APB2ENR register, sum of bit fields is bigger than 16. So implementation is LDR and SDR. First, I'm going to solve the problem for CCR1. We have to add these reserved bits to a structure. Now sum of bit fields is 15. We need 17 more bits to reach 32. So I add a bit field member with 17 bits. These are reserved bits and we shouldn't name them. And when you don't name your bit field member because it's just for occupying some empty space, it's called padding. Now compile the code. Go to debug. As you can see, instruction to access CCR1 register of DMA1 peripheral are changed. Before we had half word access with LDRH and SDRH. Now we have word access with LDR and SDR. Now if I press I and then run the code line by line, you can see when I pass this line nothing would happen. We're not gonna encounter a fault. This happened because of a change I made in bit structure in CCR1 union. Now I press F5, F5 again. This instruction is also going to cause a fault. I press F5, we're back to infinite loop. To solve this, go back to main, click on ACR, open declaration. Sum of bit field here is 6. So I have to add a 26-bit bit field member. Go back to C++ perspective, compile the code, go to debug. As you can see, instructions to access ACR register of flash peripheral are also changed. Now we have LDR and SDR instead of LDRB and SDRB. Now if I run the code, there's not going to be a problem and LED is blinking. You have to add bit field padding to all registers of flash and DMA peripherals. And whenever you're compiling your code with GCC and you encountered a fault about bit field access, solution is going to be bit field padding.